Problem B states that if cable CB has a tension force that is twice that of cable CA, find the angle theta for equilibrium and the tension in wire CB. The cylinder has a mass of 10 kilograms. We'll be evaluating this problem by making assumptions based on Newton's second law to find both angle theta and the tension of cable CB. To start, our assumptions are that there is no motion, no normal force, the mass of the cable is negated, and only force of tension and gravity are acting. What we currently know is that the tension of the cable of CB is twice that of cable CA, the gravitational constant is 9.8 meters per second squared, and the angle of cable CA is 30 degrees. The cylinder weighs 10 kilograms. We have a free body diagram on the side to illustrate the relevant forces.
We can solve the problem by utilizing Newton's second law, which states that acceleration is directly proportional to force and inversely proportional to the mass of a system. This statement can be represented by the equation F equals ma. Because we are trying to reach equilibrium, acceleration will equal 0, therefore the sum of all the forces acting on the system will equal 0. Because force is a vector, meaning it has both a magnitude and a direction, its quantities must be resolved into x and y components. This resolution can be done by using trig equations. In this case, by multiplying the forces of tension in the cables CA and CB by sine and cosine, the x and y components of the forces can be obtained. Next, we will summate the forces in the x and y directions separately, and then set them equal to 0 because mass does not accelerate. Lastly, we will plug in our cosine and sine equations, keeping in mind that the theta in cable CA is 30 degrees, and we are solving for the theta in cable CB, therefore it remains a variable. Also, we know that the force of gravity is represented at Fg, which equals W, which equals mass times the gravitational constant 9.8, yielding 98 newtons.
Step 1. Solve for the force of tension of cable CA, using the summation of the force in the y directions equation. First, note that sine 30 equals 1/2, and FTCB equals 2 FTCA. We can replace these terms. Now we can factor out the variable FTCA, and divide 98 by the term 1/2 plus 2 sine theta to get FTCA. Step 2. Rearrange the summation of the forces in the x direction. Just like in step 1, replace FTCB with 2 FTCA and cosine 30 with square root of 3 over 2. And now factor out FTCA. Step 3. Now we can plug in the FTCA we solved for in step 1. Step 4. Now we can finally solve for angle theta. Distribute the term 98 over 1/2 plus 2 sine theta and subtract the second term so the terms are on opposite sides of the equal sign. Multiply the term 1/2 plus 2 sine theta on both sides to cancel them out. Divide 2 times 98 on both sides to simplify the equation. Now we have square root of 3 over 4 equals cosine theta. Take the inverse cosine of both sides. Our theta will equal approximately 64.34 degrees. Step 5. Find FTCA by plugging in our new theta. We will get 42.56 newtons. Step 6. Now we can finally find our force of tension of cable CB. By plugging in FTCA, we will get 85.12 newtons.
To verify, first we'll insert the values we found previously into the equations and see if they balance out to 0. So, first we're going to put in our secant values, which are FTCA times sine 30 plus FTCB times sine 64.34 minus 98 equals 0. And then we insert our FTCA and FTCB values, so we have 42.56 times 0.5 plus 85.12 times 0.9014 minus 98 equals 0. Then we'll multiply those out and get 21.28 plus 76.727 minus 98 equals 0, which is approximately 98 minus 98, which equals 0. Next, we'll verify our second equation. First, we're going to put in our cosine values, so we have FTCB times cosine 64.34 minus FTCA times cos 30 equals 0. Then, once we insert the values for FTCB and FTCA and get the values for cosine, we have 85.12 times 0.433 minus 42.56 times 0.866 equals 0, which is approximately 36.86 minus 36.86, which equals 0.
In addition to our answer making mathematical sense, we can also make sense of it from a conceptual perspective. Because the system is not in motion, both the x and y components of the forces in the cable should add to be 0. In our case, they do. We also need to make sure that the units are correct. Force is measured in newtons, which is equivalent to the multiplication of the units for mass, kilograms, by the units for acceleration, meters per second squared. This yields kilograms times meters per second squared, which equals kilogram meters per second squared, which equals 1 newton. Also, we know that weight equals mass times the gravitational constant. This means we are once again multiplying kilograms by meters per second squared, which also yields 1 newton. And this verifies that all force summations are in the correct units.
So what's the real-world importance? One notable example of a real-world application of statics is the construction of bridges. Bridges must be designed to account for compression caused by vehicles in addition to the force of gravity in the opposing normal force. If the normal force and force of gravity are not equal at any point on a bridge, the bridge will be prone to collapsing. Bridges must also withstand different masses ranging from small cars to 18-wheelers. Similar to our tension setup, the forces in all directions on a bridge in an ideal situation must sum to 0, so that the bridge will remain sturdy. Other examples include power lines, cranes, and the foundations of buildings.
Thanks for watching!